Recording has started.
All right, so let's move on to lecture 14. This is again CMOS inverter, but we are going to discuss about the power and energy. So far we discussed about the noise margin and delay. Now the last piece is the power and energy. This is a reference book, Edward Smith, and the recorded materials from last spring and Professor Asif Khan. So first of all, the energy and the power, by definition, in the digital circuits, not only for inverter, but also for any digital processor. Two components. First one is this active dynamic switching energy and power. So this is due to the capacitor is being charged or discharged. To make it more specific, here the active energy is for the active computation, where the input is switching actively from 1 to 0 or 0 to 1. So here the power is measured when the input is switching from 1 to 0 or 0 to 1. That means we are doing the computation. So this inverter is driving this capacitor. So we are looking at the input having this transition, and then the circuit is consuming the power. And we will see later, this active power is this CL multiplied by the power supply VDD square, and then F is the clock frequency. This is due to charging and discharging this cap, and we will derive this later. The second component of the power and energy is this so-called static standby or leakage power. This is when the input no switching. That means the input is kept at VDD or ground, 1 or 0. So the input maintain at 1 or maintain at 0. But as we discussed in lecture 10, the transistor will have this subthreshold off current, I off. The power is the I off multiplied by the power supply voltage VDD. And this is the leakage standby or static power. Because here we are not doing computation, it's like a sleep mode of the circuit. Then the leakage is consuming the power as well. That's why your smartphone is draining the battery even in the sleep mode. This is what we discussed in lecture 10. The I off current is contributing to the leakage power. Okay, then let's look at the first dynamic switching power first, how to calculate that. So we need to think about this process. For example, in the first half clock cycle, when the input is a high to low transition, output is low to high transition. Output is low to high, that means PMOS is pulling up. PMOS is charging this capacitor. So let's use RC equivalent circuit. So this PMOS is charging this capacitor in this half cycle. That means input is falling edge. So the energy is coming from the power supply. And the charge we are going to dump to this capacitor are all coming from the power supply. So in total, how much charge is there? When the cap is fully charged, eventually the voltage reach VDD. So the charge changes from 0 eventually to C VDD. That is a charge. And all of those charge come from the power supply VDD. So the energy spent on the power supply is Q times C VDD. Sorry. The energy spent by the power supply is Q times VDD. So this Q is C VDD. So in total is C VDD square. Energy is Q times voltage. Charge times voltage gives you the energy. This is by definition. Energy is charge times voltage. If you recall our energy band diagram, we have the electron volt there. Y electron volt for energy. Electron is charge, volt is voltage potential, so electron volt is energy. So here, electron, or let's say charge, in this case is C times VDD, and then the voltage is VDD at the power supply, it's a constant. So in this process, power supply provides you C VDD square energy. This is from the power supply, but on the capacitor, because this V is changing from 0 to VDD, so the average V is just half VDD. So the energy stored on the cap will be, this is a typo, should be VDD divided by 2. In this average voltage multiplied by the Q, that is half C VDD square. Here the difference is that the voltage on the cap is changing. So on average, it's half V. So that's why you have a half in front of that. So eventually, half of the C VDD square is stored in this capacitor. Because the charges are maintained on the capacitor, then you store some energy on those charges. But if you look at the difference, the power supply provides you C VDD square, but only half of that is stored on the capacitor. Then the question is, where is the other half of the energy? You will see that the other half is here. It dissipated. So during this process, you have current flow through the PMOS transistor. If you think this is a resistor, you have current flowing through resistor. Then you are burning power there as what? As heat, right? Like a Joule heating. You have the resistor, current, then you have Joule heating. So let's summarize here. During this falling edge of the input, the power supply in total provides C VDD square energy. Half of that stored on this capacitor, half of that dissipated as heat on the PMOS. Okay. Then let's look at the next half cycle when the input is low to high transition, output is high to low. So in this case, high to low, the NMOS is working. So eventually, this voltage will change from VDD to ground. Next, the charge fully removed from this capacitor. Then eventually, the capacitor will have zero voltage, zero energy. That means all the energy stored on this cap previously, this half C VDD square, will be dissipated in this half cycle as heat through the NMOS. So this is heat, and again this is heat. Okay, so to summarize, in the full cycle, you have both rising edge and falling edge. In one full cycle, that is one full clock cycle, the energy consumed by this inverter is C VDD squared. All those energy come from the power supply. But each half cycle will consume half of that by the PMOS and NMOS respectively. But in total, it's C VDD squared in one clock cycle. And then this is due to the charging and discharging, as we discussed. And then if we want to get the power for this dynamic active switching, then we need to multiply by the frequency. Why? Because power is energy times frequency. Or energy divided by time, by definition is energy divided by time. And 1 over time, is frequency. So this is a clock frequency. And this assumes switching every cycle happens in every cycle. That means the input is switching from 0 to 1 and 1, 0 every cycle. Then the active switching power will be this CL VDD squared times F. Any questions? From another perspective, this active switching power is also consumed by this short circuit current from the inverter. So that is the current here through the inverter from the VDD to ground when the input is switching from 0 to VDD. From 0 to VDD. Then the current will have this profile. Initially, current is below the threshold current, and after you turn on the NMOS, and in this matched case, when you reach the half voltage of VDD, then the current will reach the peak. So this current is streaming the power from the power supply to ground. So it's like this short circuit current during this active switching. So this current only exists during the active switching, this short circuit current. On the other side, for the static standby power, this is due to the off-state subthreshold leakage current, as we discussed in the lecture 10. For the transistor in the subthreshold, we can draw this log scale ID versus the gate voltage. And then we have this subthreshold slope. And then here, this is I off. So this is I off. And I off by definition is when the VGS equals to 0, but VDS equals to VDD. So why do we consume this static power here? For example, if the input keep at 1, there's no switching. If input is 1, that means this is VDD. So if this is a VDD, then this is 0. So for the PMOS, the VGS is 0. But for the PMOS, the VDS is VDD. So this is the off current condition for the PMOS. The PMOS will consume this off current here. and it's off current coming from the power supply VDD. So the static power will be this VDD multiplied by this off current. This is the reason for the standby leakage power in the digital circuit. Alright, this is a summary. Two kinds of power. One is active dynamic power. This is due to the charging and discharging of the cap. And the average energy in one clock cycle is CVDD squared. And then the average power, here is F frequency multiplied by this energy, CVDD squared. But here we add this alpha in front of that. So this alpha is the switching activity. So that is the percentage of the time that the input is switching. Because not every clock cycle the input is going to switch. So we need to multiply by this switching activity factor. For example, 10% of the time the input is switching, then the active power will be 10% of this maximum clock frequency based power dissipation. So this relates to how often you switch the input. And then the static power dissipation is just this I off multiplied by VDD for one inverter. So the total power dissipation, both components, so will be like alpha F CVDD squared plus I off VDD. So as you can see here, VDD will impact the total power dissipation. So you may want to reduce the VDD, reduce both dynamic power and the static power. But there's a trade-off here. Because the delay is to the first order, like CVDD divided by the I on, the on-state current. Why is that? If you recall the TP delta T is like CVDD like to an average. So if we just think the average is the saturation current, but to be accurate will be the saturation current plus the linear current and average of that. But to the first order, it's close to the on current, saturation current of the transistor. So then the delay to the first order, CVDD I on, and to the first order, you know, I on is like mu COX W over L VDD minus VT squared. So it's proportional to VDD and then VDD minus VT squared. And then if you want to further simplify that, because you have a second order in the denominator, first order in the numerator, so overall it's like inversely proportional to this kind of VDD. So in other words, if you reduce VDD to reduce the power, your delay is going to increase. There is a fundamental trade-off between the power and the delay. This is generally true for any digital circuit or for your processor. If you change the power supply voltage, then you will gain power or then lose the delay. So there is a fundamental trade-off, and you cannot overcome this trade-off. All right, any questions? Yeah, so the switching may not occur every cycle, depending on your workloads, like your software program, depending on what logic function you are implementing. So then the switching activity factor depends on the logic function and also the workloads, what programs you are running. All right, any other questions? If not, then we're going to stop here today.